Thanks all of you for attending this. My name is Bree, and today I'm going to be talking about Kotlin generics in depth. So I first started using Kotlin about 5 years ago on kind of a skunkworks project at ClassPass, building an Android application. After we kind of put that project on ice, I rejoined our engineering organization as a backend engineer. So I've been writing Kotlin for our services, and we use those services to facilitate reservations for our members in about 30 countries. We provide fitness classes and wellness services to folks who want to work out at a partner fitness studio, gym, or go to a spa, for example. I'm happy to say that day to day I primarily work with Kotlin. We have some interpreted language as well, but in my time with Kotlin, I've really come to love statically typed languages, and so my interest in generics and kind of understanding variance and these concepts stemmed from that admiration, let's say. So without further ado, I'd like to familiarize you with some of the neat features that Kotlin provides to allow us to write rich, abstract interfaces for ourselves and then other programmers in the future. I'll be covering what variance is and how it relates to generic types, how to conceptualize type projection, how type constraints work with projection, and lastly, reification. So there's a good chance that you have interacted with a generic type, even if you haven't written a generic interface or class. A common generic type is a list. We also have maps. These are types which you can put other types into, and you'll get a kind of common interface to interact with the items in the type. You might also be familiar with the basic syntax used to define generics. On the left, we have an example of an interface with a single generic type parameter, t. And as you see, when you're defining methods or properties, you would use that annotation t to reference the type which you plan to put into this generic type at a later time. You can have multiple types. As you see with the mutable map, we have both the key and the value referenced as k and v. And then we use those throughout the definition whenever we're referencing the key or the value. So I know that's a little pragmatic and just redundant, but that's how it works. It's pretty convenient. So I wanted to get on the same page surrounding some of the nomenclature that I'm going to be using. When I actually am referencing an instantiated instance of a generic type, I'm going to refer to it as a complex type. And then the type that is taking the place of that type parameter will be called the component type. A complex type is also called a parameterized type because it is a type that has a type parameter. Additionally, if I'm referencing a definition of a class or an interface, the generic type in this case would be processor. That type parameter is often a single letter. And then, as I'm sure you're very familiar with, there are argument types and return types. So I wanted to start with variance because if we get our heads wrapped around variance, the other concepts are going to make a lot more sense. So what does variance have to do with generic types? I would say that variance defines how subtyping between complex types relates to subtyping between their component types. And then we use variance annotations in Kotlin to enforce these relationships at compile time. So if you use a variance annotation, the compiler is going to start to tell you what you can and can't do when you're writing other methods, and this will inform other programmers as well as yourself in order to enforce these kinds of relationships that we're trying to define. So I wanted to give you an example of a situation where the compiler is using the concept of variance to prevent you from doing something that might hurt you, so to speak. If you, for example, had a list of strings, you would be able to assign that to a list of any. And that's because a list of strings is a subtype of a list of any. It makes sense. You kind of look at the two, you're like, okay, a string is a subtype of any. I think that the lists are also subtypes of one another. And if you brought that same mentality to the table when you were looking at a mutable list, like in our second example, you might be confused when the compiler says you're not allowed to assign that list of mutable strings to the list of mutable any. And that's because while you can pull items out of this mutable list, you will not be able to put items in without potentially breaking the type safety. You could assign a number to that mutable list of any, and then when you're trying to pull strings out of your variable strings, you'd get a number. So in this way, the compiler is protecting us from situations where we would have runtime exceptions. There are 3 types of variance, and I'm going to first go through what they are conceptually, and then we'll talk about how we can ascertain which type of variance we're looking at, and then lastly, how you can specifically annotate your classes with the kind of variance that you would like to have. So the 3 types of variance are covariance, where the complex type, that list of items, subtypes in the same direction as the component types. So as you can see with the example of a flock of ducks and a flock of mallards, a mallard is a subtype of a duck, and so the flock of mallards is, in this case, in this image, a subtype of a flock of ducks. That would be called a covariant relationship. If the complex type and the component type subtype in opposite directions, we would refer to that as a contravariant relationship. And then lastly, if there's no subtype-supertype relationship at all between the complex types, that would be invariant. So kind of like thinking about that initial example where a list of strings is a subtype of a list of any, that, just at a glance might make intuitive sense. But if you were to ask yourself, like, how can I identify if a subtype is a subtype? You would probably turn to some rules that software engineers have come up over the years. So one that you may be familiar with is Barbara Liskov's substitution principle, which kind of generally reads that subtypes should conform to the behavior of their supertypes such that the subtype could substitute for the supertype without breaking the program. So in this case, the string is going to have all of the same behavior as an any, and in that way we can substitute them safely. We can break that down a little more, though, and I like these rules that David Leeds put on his blog. It's typealias.com. It's super great. There's a bunch of really cute comics in conjunction with information about a bunch of neat Kotlin features specifically. So it's a Kotlin blog. And the rules that Dave has on the subject of variance are that in order to ascertain if a type is a subtype, you have to kind of like check these rules. And the rules are that subtypes have to accept argument types the same range of types that the supertype declares. And then when we're thinking about return types, the subtype has to return at most the same range of types that its supertype declares. If it returns an animal but you're expecting a duck, it's not a subtype. So it's kind of easy to test these rules if we have the types explicitly defined. So I wanted to go through an example where we just have those types written out and we can do the comparison and contrast to kind of start thinking in subtypeness. So in this example, we have a flock of ducks. You can add a duck to it. You can get a duck out of it. And then you have a flock of mallards, which allows you to add a mallard or get a mallard out. And we're just going to check if we could make the flock of mallards a subtype of a flock of ducks. And we'll run through the rules and see if the flock of mallards interface conforms. So if we're looking at the argument types, we would initially fail the first rule. The subtype has to accept at least the same range of types as its supertype declares. So in this case, a mallard is more specific than a duck, so it's not the same range, and we're not able to say that the flock of mallards is a subtype of a flock of ducks on the argument type specifically. However, if you turn the interfaces around and you say, is a flock of ducks a subtype of a flock of mallards, you'll actually find that it is, and therefore there's a contravariant relationship between the argument types and these complex types on the arguments. If we turn our attention to the second rule, though, and we're just looking at return types, you'll find that the rule passes, the subtype returns at most a mallard, which is at most a duck. So we can safely say that these interfaces are covariant on the return types. So now let's take that example and turn it to use generics instead of having explicitly defined types. So now we're using T, and we have a flock. It returns whatever you put into the flock, and it also accepts it. So I'm just going to kind of do the exact same thing and show how we can run the test. If we have a duck and a mallard, you'll once again see that there's a contravariant relationship on the argument types. Flock of mallards is not a subtype of a flock of ducks. But if we look at the second rule, it passes again, so there is a covariant relationship on the return types. So ultimately, like, what does this mean when we pass one of the rules but not the other? And in this case, it means that there's an invariant relationship between a flock of mallards and a flock of ducks. There's no subtype, supertype relationship whatsoever, so we can't expect to substitute one for the other in our code. So I mentioned that I was going to cover variance annotations, which lets us specify the kind of variance that we want a class or interface to have, and thus inform other engineers what they can do or can't do with the class or interface. So if you wanted to create a contravariant relationship, like the list of strings, being a subtype of a list of any, you would use the in keyword on the type parameter. You can think of in as an input or inconsistent because it's contravariant. Contrary and inconsistent kind of line up for me. There's a bunch of different mnemonic devices you can use. Hopefully one of these resonates with you. Contravariant types are also known as consumers or sinks, and that's because they're write only. You can only put things into them. If you were to specify the contravariance on the type parameter t, you would not be allowed to add any methods to this interface which return that type. And the compiler would enforce that on you. And in that way, you would know that a flock of mallards is a super type of a flock of ducks. Kind of weird, but that's how you enforce it. A covariant relationship uses the keyword out. This one I find is easier to remember if I just use the concept, or not the concept, the pronunciation covariance, co as an out. The covariant types are also called producers or sources because they're read-only. They can only send that component type out of them, but they cannot receive them. So immutable list would be a covariant type. I think I may have mentioned the immutable list regarding contravariance, and I meant to be referring to it on the covariance slide, so apologies if that was confusing. Once again, the compiler is going to keep us from sending any of our component types in to the flock if we were to suggest that it is a covariant relationship. And lastly, invariance is what you get when you don't specify out or in. So if you've defined a class with a type parameter, but you've never bothered to specify out or in, you're getting invariance, and there's not going to be any subtype, supertype relationship between any instances of the complex types in your code. In the world of Java, people use this acronym PEX, producer extends, consumer super, and that's because the syntax previously was wildcard extends, and you would specify the type that it extends, and this would allow you to kind of specify what that covariance contravariance relationship looked like. JetBrains is suggesting that you kind of throw this out the window, and I would say that there's not a different acronym to use, but the goal being that in and out are kind of self-explaining. If you're using in for contravariance, you can only put items in. If you're using out, you can only take things from it. It's read-only. So if we wanted to make that flock covariant, we would use the out annotation. And in this way, both of the subtype, supertype rules would be satiated. We could interact with this flock of mallards as though it's a flock of ducks. So if we go back to the first example, hopefully it makes a bit more sense as to why you can't interact with that list of strings as though it's a subtype of a list of any. The list of strings, the mutable list of strings is invariant, and therefore there's no subtype, supertype relationship, and we can't do this kind of substitution safely. So now that we have, hopefully, a handle on variance, we can talk about type projection, which is also called use site variance, and then we'll also discuss star projection. So when I was describing the kinds of variance, I personally quite like covariance, but invariance is also useful. A mutable list of strings is nice because you can put things into it and you can take things out of it, but maybe you sometimes want to interact with that mutable list of strings as though it's a subtype of a mutable list of any. And one way that you might think to do this is to create multiple interfaces. You have a writable flock and a readable flock, and then you just have a flock which extends both of those. And in a situation where you want to use the readable flock, for example, you just use that interface, which would allow you to pretend or not pretend, but it would allow you to use a flock of mallards as though it's a flock of ducks. And I would say you don't have to do any of this because use site variance lets you specify it at the call site. So when you're defining that function or that method, you can use type projection to turn a flock of invariant ducks into either a flock of covariant ducks or contravariant ducks, and then use it as such. So what does this actually do under the hood? Like how does the compiler kind of ensure that we do the things that we can do safely with those covariant or contravariant types? And what it does is it basically creates an interface of the generic type inside of the function or the place where you're using the projected type, and it would look something like this. In the case of the read-only flock, any of the argument types will be converted to nothing. And you can't possibly give a method nothing and have it be happy, so effectively those aren't usable. And then conversely, if you were to try and pull anything out of a contravariant type, you would get a nullable any on the return types. And once again, a nullable any is basically useless. So you wouldn't be able to interact with it as though it's covariant. I'm just going to flip around the implementations of these read and write functions so we can kind of do an exercise and see what would happen were we to try and write code that contradicted the kind of variance that we had described in the useSite annotation. So in the case of the contravariant flock, the readable flock, if we tried to insert something into it, the compiler would tell us that it requires nothing, but it found a duck. So it's not actually going to explicitly reference variance or the variance annotation when it warns you, but this is the kind of warning that it will give you, and hopefully when you have a grasp of variance and the kinds of things that you're allowed to do when working with these variance annotations, it will make a bit more sense. If you were to try and read something from that covariant flock inside the write function, it would tell you that it requires a duck, but it found a nullable any. So there are situations where you might want to put something in to a covariant flock, and in this case, it would be just to find out, for example, if that flock had a member. And so because the compiler is going to say you're not allowed to do that, this is a covariant flock, like please stop, there's an annotation that will let us get around that. And this is the same annotation that is used in the immutable list definition. So if you were to go look at that today, you would see this unsafe variance annotation. It's scattered throughout immutable collections, and it basically just allows us to see if those lists contain one or many instances of the component type. So that's the covariant, contravariant uses of type projection. But there's another kind of type projection called star projection. And if you've written a lot of Java, this is also known as a kind of wildcard. I'm not going to reference the Java implementation because it will just distract. But the asterisk here references that we're using a star projection. And what that basically means is when we call the members of this flock, the type parameter t is going to be available to us inside the function getNames as though it was a contravariant any or a contravariant nothing or a covariant nullable any. And so what this ultimately ends up being is an interface that we really can't do much with except call toString or the other kinds of methods that would be available on a nullable any. So an example that comes to mind is, let's say you have a list of items, you have no clue what's in the list, but you want to log out what's in the list because you're debugging or you just want to kind of introspect it. You could use a star projection on the list and then use the toString method to log, and in that way hopefully find something out about what's actually going on. So I also mentioned that I wanted to cover the concept of type constraints. And I'm going to do so in the context of star projections, because I think it will kind of also explain why you should use star projections or use site variance, as opposed to some of the other ways that you could conceive to do this stuff. So in the case of this flock, I've now added an upper bound constraint of duck. And that just means that at most we can put a duck into this flock, and if we try and put an animal, for example, it will say, no, please don't. That resulting type projection will now carry the duck through to any of the places where we would have had a nullable any. And this means that we can add methods to a duck that we can then call once we've star projected it. So in this case, I've added this method hasEgg to the interface duck, and I've changed our getNames function to be getEggs, and it basically just retrieves all of the eggs from the list of ducks. So if you had alternatively used in nothing or out any as your use site variance annotation, instead of that star projection, that upper bound of duck wouldn't have been carried through into the function itself when you were trying to call it. So you would be getting a nullable any, and therefore you would still only have toString available to you. And so this is like hopefully kind of explaining why it's better to use the upper bound constraint and star projection as opposed to use site variance to kind of do the same thing. It would work, but you wouldn't get as much functionality. Another way to do this in terms of adding an upper bound constraint would be rather than specifying it on the flock itself, you could specify the upper bound constraint on the function here. So the last line of this slide shows a function getEggs, which has an upper bound constraint of duck. And this would allow us to interact with the items of that flock as though they're ducks. And I would say this is super valuable if you don't actually have access to the code that you're trying to extend. So you could write an extension method on a list, for example, which has an upper bound of number, and you could add a specific kind of sum method, for example. And then inside that method, you would be able to interact with all of the entities of the list as though they're numbers at most. So in this way, we can modify libraries that other people have written using extension functions, which is not something you could do if you're trying to modify the interface or class itself, because you wouldn't have access to it. So when thinking about star projection, you might have thought, why don't we just use nullable any as the type that we specify when we're trying to relay like what can go into the function. I've provided two examples here. We have a list which is covariant, and it uses star projection in the first method or function. And then we have a function which allows you to send a list of nullable any in. And this works the way you would expect because a list is covariant. You can send that list of strings in, and the compiler is going to say, a list of strings is a subtype of a list of nullable any. You're good to go. But if we tried to send an invariant type in, like this flock, the compiler is going to warn us. It's going to say, I require a flock of nullable any. You're providing a flock of ducks. There's no subtype supertype relationship between the two, so please do it a different way. And so this is, you could basically think of this as nullable any at the argument definition would act as a validator of sorts, whereas star projection is going to take anything in, but then it's going to project it to what we want. So inside that function, read flock with any, well, first off, we wouldn't be able to call it, but if we then looked inside the read flock with star projection, we would get a mutable list of nullable any's and the star projection behavior that we would have gotten before. So lastly, I wanted to talk about reification. The word itself might seem confusing, so I provided a definition here. To reify is to make something abstract more concrete or real. And in this case, what we're going to be trying to reify is those generic type parameters in our actual complex types when we're working with them. So I wanted to provide some examples of situations where you might find yourself grasping for reification. So this example allows us to send an instance of anything into the function. This is string function, and then it does a comparison. So we're able to see that in this case, this empty string is a string. Another way to do this would be to send in a K class, and we could send in the strings class and do a comparison and be like, okay, the string is a string. But once again, you have to send in the K class. It's kind of clunky. You're specifying, : class. we could just try and get the type from the type parameter. So if you were to write a function like this that specifies t as the type parameter, and then you tried to call class on t, you wouldn't be able to, and that's because of type erasure. Type erasure exists because the JVM has to support older versions of Java that didn't have generics in them. So basically, at compile time, we know this information, but at runtime, we don't. So the way that Kotlin gets around this is it actually allows us to reify complex types using inline functions. So if you wanted to reify a type parameter, you would first make the function or method inline, and this is going to come at the cost of copying that piece of code around when we're compiling the program. If you're not super familiar with inline functions, just know that it basically, as I mentioned, it kind of takes that piece of code and it inlines it in the bytecode over and over at each call site. So it creates a copy of the implementation at the call site. And what this does, as far as reification goes, is it allows us to reify those generic types because when it copies the code, it's going to include the type in the bytecode. So we add the reified keyword to t here, and then we can call class Java on this type parameter t, compare it to a duck, and we will see that in this case, well, I've put string down at the bottom, but that would be false, and so would the empty list. I wanted to mention regarding the empty list how reification is valuable. So if you had a list of an unknown type, or maybe it's a set of types, and you wanted to have different behavior based on what kind of type was in the list, you might think, oh, I'll just grab the first item of the list, and I'll see, is it a type duck, or is it a type mallard, and then do something different with it. And that works so long as the list has items in it. But if the list is empty and you still want to kind of go down a different logical path, you can check the type using reification. So you can check that empty list and see that it is supposed to be an empty list of ducks, but right now it's empty. I wanted to just show what the bytecode looks like. So this is the decompiled bytecode. This is the actual Java that you get if you use IntelliJ, for example, to take your Kotlin, turn it to bytecode, and then you can decompile it. And this is kind of where the magic happens. In this case, there's a comparison between duck class and duck class, so that would result in true, and we would be able to reify that generic type. An example of a place where this is pretty pervasive is in deserialization and serialization libraries like Jackson Module Kotlin or Jackson Object Mapper. Oftentimes you'll have a situation like here at the bottom where you're trying to read a value from a string of JSON, for example, and you want to kind of do a deserialization cast into a native object, in this case duck. So we can get that behavior without passing the explicit duck class into the method. And that's reification. Hopefully that made sense. I'm kind of a little under time, obviously. But if you have any questions, please feel free to ask them or find me after or tweet at me. And I'm going to put these slides on my Twitter. So if you want to get any of that content, it will be available there. Lastly, I would say these sources were super valuable to me when I was learning about this stuff, and I would hope that if you have an interest in it, you check some of these out because they're really great resources. So thank you. I appreciate you all coming to learn about generics.